Hi everybody, so my name is Frank Maker. Thanks for coming out. Tonight I'm going to talk to you about power profiling. My hope is that by the end of the night you'll have a good idea of what your options are if you need to do some power profiling for your applications. Before I get started and tell you a little bit about myself, wanted to get some feedback about who the audience is. So QA and testing and application development, looks like it covers it all. Okay, good. So I think this talk will fit your needs then. So my name is Frank Maker, as I said before. I'm a PhD student at UC Davis. I'm almost finished, so hopefully I'll be able to say PhD soon. My PhD dissertation is about how to adapt software on smartphones for fixed energy constraints. And so all the papers and all the work that I've done are focused on the problem of how do you adapt software to different energy conditions. So in order to do that, a big part of the work has been profiling apps, doing power measurements, things like that. And I'm actually not in the computer science department. I'm in the electrical engineering, computer engineering department. So I have some, academic background in electronics and whatnot. So I brought along a little oscilloscope I'll show you later. But if you have any questions, kind of electrical-wise, I can probably handle those as well. So my background related to mobile, well, actually, in general, let's see. I worked for Motorola Automotive for a couple years when I got out of undergrad at the University of Rhode Island. When I was an undergrad, I worked in BMW for a few summers on engine control units. So I've been working in embedded software for about 10 years now. And then when I came out to California, I switched over to mobile. So I did an internship at Broadcom working on their Android device. Any of you have that Roku box, the low-cost one? I worked on that, getting Android set up on that. And then the summer after that, I worked on the Google Android team, writing an obscure little networking library that nobody will ever notice other than a system engineer, but I thought it was fun. And that's basically where I'm at. So if you guys could, do you have any questions before I get started? Okay, all right, let's get started then. So we're going to talk about power profiling. So this is the outline of the talk. First thing I'm going to talk about why you want to do power profiling, which to many of you may be redundant, otherwise you wouldn't be here. I'm going to talk about the mobile platform in general, and specifically how it's different than a regular computer. Because a lot of you probably went to university and learned about general purpose computers, but smartphones were were a very different animal back then. So I'm going to give you an idea of actually what's under the hood so you can better understand from a power perspective how things are different. Then I'm going to talk about power profiling specifically and how it's done. And I'll go into a few different methods that you can use, and then I'll be doing a demo with an oscilloscope, and also show you how to read the current using the internal current sensor on the phone. Okay? All right, so we'll start with the motivation. So the main problem with power on smartphones is that the batteries just can't keep up with the smartphones. And this isn't a problem so much of research and development time. It's really, there's some physical limitations involved. So what this chart shows you up here from Next Energy is that the lithium ions we have, which are in this area right here, are roughly in the middle of the pack in terms of the weight for a given watt hour. So watt hour is a unit of energy. So the amount of energy you get for a given kilogram, and then the density, how much energy you get for a given liter of volume. They're roughly in the middle. So in the future, we might be moving to something like a zinc air battery, lithium air I've heard a lot about. But right now, we're stuck right here. And that's why your battery isn't going to get tremendously better, because there's just limitations on the chemistry itself. And a smartphone has a fixed volume, so it's not like you can just keep throwing more and more material in there. What the manufacturers seem to be doing, as far as I can tell, is they try to make the phone smaller and the battery bigger, which is one way to do it. But there's just a limit to how far you can go. So the reason you can't go much further is because the smartphone is air-cooled. So there's only so much energy that you can dissipate inside the device with that volume without having to do something like forced air cooling, which is what you would do in a regular computer. So in a regular desktop computer or even a laptop, you have a fan, the fan blows air, the air wicks away the heat, and that allows you to dissipate up to about 80 watts of power on the CPU. But on a mobile device, you don't have a fan. And it's also much smaller. And it's in your pocket. And sometimes it's on your dash. So there's a lot of scenarios where you can't get rid of all that energy. So that's the main problem. The batteries are not getting tremendously better. So 30 to 40% per year might sound pretty good to you in terms of battery technology increases. But you have to ask yourself, do you think your smartphone is using 30 to 40% more power each year or more? I'll tell you, it's quite a bit more. When you go from the old Symbian phones where you had your WAP browser and maybe you could see a few movies that were playing to seeing YouTube high definition 1080p videos, you're going a little faster than 30 to 40% a year. So the batteries just can't keep up. And to make things even more interesting, the capacity fades over time. So a lot of your customers, if you're writing applications, they might have a pretty good sized battery to begin with, but then a year, 2 years later, some of us are crazy and keep our phones longer than 2 years. Their battery is much lower, so now they're going to put even more of a premium on their battery life. So all around, it's a big problem. And to give you an idea of where the power goes, I put up this table from a paper at ISSCC, that's a major circuits conference, which just gives you a breakdown of roughly where the power goes inside the device. So this is going to vary between manufacturers, but this was from a man from Nokia back in 2004, so it should be reasonably close to what it would be today. And the main one is the cellular, so that would be the baseband. So that means anytime you're making phone calls or doing data over the cellular radio. So that's the big one. The next biggest one is the application processor. And you'll notice I call it application processor instead of just the processor, and that's because the cellular is also known as the baseband processor, because those are both two big processors in the device. But the difference is that you never program this one. You always program this one. If you program this one, you work for a company that licenses the IP to communicate with the cell phone towers. And if you don't, you guard this like crazy. So this is the one you're always working on. The memories actually take a decent amount of power because they have to retain state. So you have DRAM inside phones, and those DRAMs have little capacitors in them, and they have to be continually refreshed in order to hold the memory. So that takes a decent amount of power. And then there's user interface, which would cover the display, the backlight, buttons, LEDs, that sort of thing. Audio can also be kind of a second order power here. And then the rest is other components like Bluetooth, the power manager chip, etc. So Bluetooth is actually very power efficient. So if you ever have the option to use Bluetooth over, say, Wi-Fi or cellular, you definitely should. Somebody else had a question? Miss?
Where do GPS and location-based devices appear?
It's probably somewhere into the other. GPS isn't that bad. Actually, GPS was the fifth one. Thank you. But the other thing with GPS is it's not. How do I say that? It has a different draw. Basically, the power varies quite a bit based on whether you're receiving a lot of location updates or just a few. Because the power for GPS, there's like a baseline just for having GPS on, and then there's a little peak for each time you receive a location where you have to do these computations to figure out what the GPS satellites are telling you. So it's kind of a hard thing to give just one number on because it's going to vary dramatically whether you're here in San Francisco or if you're out in Oklahoma or something. Okay, so just to once again drive home the physical limitations here, I just put up some stats about the difference between a smartphone and a laptop, just to give you an idea of how much dramatically smaller we're talking. So the power budget for a smartphone is about 3 watts, as I told you, and for a laptop around 60 watts. So you can see the size here, and then the volume is about 91 cubic centimeters versus 1,500-ish cubic centimeters. So this is dramatically bigger than this, and you can do forced air cooling. So that's why you only get 3 watts here, but then you get 20 times as much power here. Okay, so now we'll lift the hood a little bit, give you an idea of what's inside a smartphone. So inside a laptop, you essentially have a big processor. I don't know if they still have Northbridge and Southbridge as separate chips, but there's not that many chips anymore. Most of it's been sucked right into the general purpose processor. And the reason is because almost everything's done in software. Your audio is done in software, video is done in software. Almost everything that can be done in software is done in software. But on a smartphone, because you only have this 3 watts to play with, they break out some of the more energy-intensive functionality into ASICs, application-specific integrated circuits. So basically, application-specific chips. And so this is a picture of what a what's this phone called? Nexus 4. What a Nexus 4 looks like inside. So you can see the system on a chip. System on a chip is the for those of you more familiar with a general-purpose computer, it's the main processor plus a bunch of ASICs that the SoC vendor bundles in. GPU is usually inside there, maybe multimedia codecs, things like that. But then you have some other chips as well, the baseband, like I was talking about. So this does all the cellular stuff. And this is actually, this is usually an ARM core. There's some x86s out there now as well, but this is typically an ARM core, maybe anything up to like an ARM 9 Cortex A9. These tend to be an ARM processor as well, but a little bit slower because they don't need as much performance. Because this chip is running is a real-time chip, so everything has to be done at a certain time, and there's deadlines that need to be met by the software. That's what real-time means. Whereas this chip is where your software goes and the operating system, and all that stuff is just best effort. So that's one of the reasons they split it into 2 chips. And you might have NFC, which is in green in the upper left there, an audio chip in pink, the power manager, which is in black. I don't see it. Is it really in black? I think it's actually in yellow. That might be a typo. But anyways, what the power manager does is it just changes the voltage for all these different chips in order to reduce the total power. You don't really have to know much about that. And then on the other board here, you have a flash memory, which can be pretty big, gyro and accelerometer. Those are reasonably power heavy, considering you run them for a long time. Power amp for the cell phone, and then the Wi-Fi and Bluetooth are usually bundled into a combo chip, and that one is in pink. So as you can see, on a normal computer, all this functionality would be inside the one chip. But on a smartphone, they've been spread out into different chips. And that is basically so that they can go inside to these chips and custom build the transistors inside the chip to do that one purpose and do it energy efficiently. Whereas Intel just throws it all on one chip. They throw the fan on, and then they do it however they feel like doing it. Or they might throw on some extra instructions to make it work better, you know. But they have a lot more headroom to work with. So here's another example. I'm not going to go through this one, but this is an iPhone 3G. So you can see it's pretty similar. Now you can notice the difference between an Apple design and a Google design. Well, not Google, HTC. So you see on HTC there's a lot of green, there's some green openings. I think the biggest openings here are like this and this. And I saw a picture of the latest iPhone, and it was actually even smaller. Like they really don't waste any little bit. It's pretty amazing. I mean, this layout is just ridiculous. I would not want to be the person in charge of this. This is a hard layout. As time goes on, the process technology will scale. It'll go down. So every year and a half, the fabs will shrink the chips. So you get some savings from that. So like if you go to the next generation, you might be able to recoup like, I don't know, another 20% just on the chips getting smaller. But in terms of the efficiency of it, I mean, it's just a very difficult design to do because each one of these, especially the big chips, could be putting off a serious amount of power. And then that heat is going to spread over to the passive components here, and then you got yourself a modeling nightmare. But, it makes sense because it can only be that big, and if you can squeeze all that functionality in, people are willing to pay for it. So, does that answer your question? Mm-hmm. Okay. Okay, so now power profiling. So why would you want to do power profiling? One, I'd say the main reason is for application design feedback. So you're designing an app, and the app, you don't want the app to use more battery than it has to in order to give a good experience to your customer or whoever installed your application. And so you need feedback on different design decisions. Does code A take more power or code B, that sort of thing. Driver development would be another one. So if you're working for, especially if you're working for one of these platform companies like Intel or Samsung or one of these companies that makes the actual chips, you can use power profiling to tweak your drivers and decide what your tail states are going to look like and things like that. And then runtime adaptation is one that I've looked at. I haven't seen much of this done by people in practice, but the idea is if you can measure the power on the phone itself, you could actually adapt your software at runtime. So if you notice the cellular, so say you really want to use cellular like you were talking about, but you give a, you're going to put a limit on how high you're willing to let the power go. If you're able to measure the power on the phone, you could do that. So you could actually have your device, maybe it's sending data back to drive ads or something. But then once the power gets over like 750 milliwatts, you decide, OK, I'm just going to stop and I'm going to wait till the power comes down, something like that. So those are the three reasons for power profiling that I could come up with. So now I'm going to talk a little bit about what power and energy are, just so we're clear on our terms before I get to how to actually do the measurements. So feel free to ask questions, because people find this can typically get hung up on this. So power is a rate of electrical energy. So it's like how much the electrons are moving and how fast they're moving to give you a certain amount of power. Energy is actually the work being done. So I like to explain this with a driving analogy. So you can think of power as the speed that your car is going. So if I tell you I'm going 50 miles an hour, that doesn't tell you how far I've gone. That just tells you how far I was going. That's just tell you how quickly I was moving. But then energy is the distance traveled. So energy is often what people mean when they say power, because energy tells you what you actually did. So if you ask me how much power does it take to send 50 kilobytes, I can give you an average power, but I can't tell you how much energy it takes. The power can't tell you how much energy it takes to do that task, because that's an energy measurement. Because the energy is going to look at how the power fluctuates over time and take that, and that is how much it actually costs. And so power is measured in watts, and energy is measured in joules. Then I only have two equations here. I'm sorry. I'm still in academia, so I have to have some math. So a joule is just 1 watt per second. So it's the number of watts times the number of seconds. And so energy, and we said energy is measured in joules. You can also look at the integral of power over time, which is the same thing as saying the average power times the change in time. So if you want to measure power, then you just hook up the scope or look at the current sensor on the phone like I'm going to show you, and you have your power. But usually what you want is the energy, because the energy is going to tell you between two different, say you're measuring two different ways to do some algorithm, it's going to tell you that if you just look at the power, that's going to tell you how hard the processor was pushing in order to run the software. But what if one of those pieces of software runs a lot more quickly than the other piece? So if one uses twice as much power but takes half as much time, and the other one uses half as much power but takes twice as much time, you need to be able to compare those two. They might be the same, So time is an important factor to consider when you're measuring power. Is that clear? Okay. So the first method I'm going to talk about to do software measurements is with a software model. And I would say this is can you guys see this at all? It's as big as I could make it. This is a copy and paste from an academic paper, so I couldn't make it any bigger. So a software model is probably the most accessible to everyone because it doesn't rely on any physical measurements of the phone. You do the measurements offline, so you can use something like an oscilloscope or a monsoon, or I'll talk about some options. And you can store all those measurements in a table and then use them to do your calculations either in the software or just by hand to estimate the power. So this is one that was published by some people at University of Michigan. And what they did was they looked at, this is for an HTC Dream phone, which is the first Android phone. Remember the big blocky one? So they looked at a few different components, and they basically came up with constants. So that's these coefficients here. And then they plugged them into a linear model. So it's just a coefficient times a number. and then add those all up, and they're able to estimate the power. So you can actually download the app that these guys made. It's called Power Tutor. Or you can search for this paper here too. So they'll be posting my presentation online if you want to look this up. So if you download their app from the market called Power Tutor, you can actually run this model on your phone and see how much power your phone's using. Now, it's only going to be reasonably accurate if you have an HTC Dream phone. So if you have another phone, it might give you a rough estimate, but if you really want a good model, you'd have to calculate these power numbers out yourself. But there's other models that have been published as well. So if you find someone else's software model, like Google, for example, they have a software model built into Android. That's how you get your battery usage screen. The problem there is they don't give you the numbers unless you have one of the Nexus phones, because the manufacturers don't want anybody to know those numbers because they don't want anybody to know anything that might potentially cause them a problem. So.
Excuse me. So you're saying that
Sure.
Nexus phones do give you the number?
Yeah, so you can go, I can show you after the presentation if you like, but you can go into the Android open source code and find the XML file that has their software model numbers. So if you have a phone whose source code is in the Android open source project, then you can find the constants. Otherwise, you'd have to go get them yourself. Or I suppose you might be able to root your phone and get it that way too, but that's, depending on what the Supreme Court says, that may or may not be legal. I think it's currently legal, but we don't. It's shady. And there's another approach which is very high accuracy, but also very difficult to do in practice, which is system calls. So there was a guy from Purdue that wrote a paper making a model just on system calls. So every time a system call was made, he assigned a certain amount of power to that, and he would look at the state that the system call was in. So this is your Rolls Royce of power models right here. But that's going to take a lot of effort. So if you're just one developer, it's definitely not worth your time. But if you need something more precise, then a system call method model is currently the best you can do. Okay, so that's a software model approach. So another approach is to do internal measurements. Internal measurement uses the battery monitor unit inside the smartphone. So the battery monitor unit is in charge of controlling charging and discharging in the device. So it's the chip that decides how much power to send to your battery when you plug it in, for example, because if it's full, it needs to stop sending energy. But what it also does is it tells the system your estimated remaining battery life. And so in order to do that, it has a little current sensor inside it, which measures the current and then feeds that into the model in order to give you a good estimate of how much remaining battery life you have. Because the system needs to know how much battery life you have in order to shut down cleanly if your battery life goes too low. So the picture I have here is from a Nokia app. This is for the S60. So I haven't seen an app I haven't seen any apps for any of the modern smartphone OSs that do this, but the Nokia platform did have one. And what it does is it graphs the reading from the current sensor as it comes in. So now this probably looks pretty good to you, but one of the problems with these sensors is that they have a very slow update rate. So the time difference between any of these 2 points is actually 250 milliseconds, so a quarter of a second. So in terms of telling you precisely what the power is, the measurement's going to be off by a good bit. But in terms of giving you qualitative feedback between where the power is going, how much it is, it's probably pretty good for that. But you can't use it unless you're doing Symbian development, so sorry. But some Android phones do have these current sensors, specifically the ones from HTC. So I have an HTC Nexus 1 over here that has one in it. And I'm going to show you how to see the current on here, but you basically have to look at the particular device you have to see if it has the current sensor in it. But because all the Android devices, for example, run Linux, it'll be in the same place as I show you. So if it does have it, it'll show up in a similar path. But for iPhone, I don't know what they have. So is anybody doing any other platforms? Like BlackBerry maybe? No? Windows? Poor Windows Mobile. No love. They actually came to Davis a couple weeks ago, and they gave out pizza and Microsoft-y garb and all that stuff. And they were giving out $100 to any student that wrote a Windows Mobile app while they were there in the class. And I walked by there because I had to go home to pick up my kids. And there was only like 10 people in there. I felt so bad. I'm like, they're giving away money and like still nobody will come. I feel bad for them because Windows Mobile is actually a pretty nice phone, but it just doesn't seem to be catching on as much as they'd like. Okay, so the last method, which I think is the most likely for all of you, is external measurement. So that would be using some sort of benchtop equipment. In order to do that, you can either use a Monsoon, which is a device that's specifically designed to do this for smartphones. That's what this picture is here. And I included the URL here in case you want to buy one. I think it's about $500. So, sorry, $800 now. Okay, used to be $500. Okay, they're making a nice little profit up there. So if you buy a Monsoon, that'll definitely fit your needs. If you want to do something a little more lower cost, for example, this oscilloscope here I bought cost $300. So, and it works just fine. So what you need to do is you need to set up a current sense resistor. So find your friend that likes to do soldering and get them to solder a resistor for you if you're not into that. And basically what you do is you hook the resistor up between the positive rail coming out of the battery, so the positive side of the battery. You connect the resistor between that and the phone. So that way the resistor is sitting in between the phone and the battery. And then because of Ohm's law, which some of you may be familiar with, you can basically measure the voltage on this resistor, and it's proportional to the current going through the resistor. And since the same current is going through this resistor that's going to your phone, that's your measurement for your phone. So I actually have this set up here on my phone, so if you want to come take a look at it after, you can feel free. But that's really all you have to do. And then you measure here for voltage, because power is voltage times current. So you measure here for voltage, and then you measure across the resistor for current. And if you multiply those two together, you have your power. So pretty straightforward. So I just want to give you a couple tips, and then I'll do a demo showing you how to read internal current measurement and then external with the oscilloscope. So the first tip, I found that a 100 milliohm current sense resistor worked pretty well. So I tried a 10 milliohm, and the signal was really small, and it was hard to pick up on my oscilloscope. So as a rule of thumb, I'd recommend the 0.1, because the higher you go with the resistance, the less power you're leaving for the phone. So if you make the resistor too big, the phone won't even turn on. So this value worked pretty well for me. The resistor itself, you're going to need, so package is the name for the type of resistor, because there's all different types of resistors based on how much power they're designed to handle. So you need one that's 100 milliwatts or more, roughly. If you're using a power supply, so in this diagram I showed just using the smartphone battery, and you're just putting the current in the middle. But you could take the smartphone battery out and use some sort of power meter, like a, not power meter, power supply, thank you. So you could use a power supply here as well. If you do that, make sure to set the current limit, because if you accidentally touch something, you could fry your phone. So when I first started at Davis, we had this box of about 50 phones, and my first couple weeks there, I fried like 5 until I started setting the current limit. So what the current limit does is it tells the power supply, don't give any more current than this, because you might need to go up to 1 amp, maybe if you're doing cellular stuff, because you'll have these little tiny high amp pulses, but certainly not over 1 amp. If you're doing more than 1 amp, then something's broken in the phone. I used copper braid for the connections, so any of you that have ever done tinkering with soldering irons, copper braid is this really flat metal wire. So if you go into Radio Shack and you ask them for copper braid, you'll find it. And then the nice thing about copper braid is, since it's so flat, but it's conductive, you can squish it in between the battery and the phone, so you don't have to solder to anything. And that means the setup I have here is with copper braid. You can see the coppery color here. That means if I take everything off, take all the electrical tape off and everything, the phone looks the same as it did before I started. Because what I used to do before I knew about the copper braid was I would solder directly to the battery, which means now the battery can't be used the way it was before, right? Because now I've messed up all the pads, you know, the plastic is melted and things like that. But if you use the copper braid, then you're good to go. Tape down the probes. I'm surprised it took me like 5 years to figure this out. But if you just tape down the probes, then they don't wiggle out. And the phone doesn't get shorted, and your measurement doesn't get messed up. If you don't tape the probes, then you're going to hit it, you're going to bump it. So just tape down the probes, and you won't have any trouble.
5 years?
Yeah.
Interesting deal.
Just one day I was like, I should just tape this down. And then another nice trick is using ADB over Wi-Fi. So you can download an app. There's a few of them on the market that will allow you to run ADB over the Wi-Fi interface instead of USB. And what that lets you do is unplug the charger here, unplug the USB from the phone. And the reason you want to do that is because the USB is going to charge the phone. So you're going to get positive current measurements. So you're going to think that you violated, some basic law of the universe because you're getting more energy out than you put in. But it's really because you have it plugged into the computer. So if you want true current measurements, you have to unplug it with USB. And I found Wi-Fi over ADB was pretty useful because then you can load the program that you're going to test. You can get some debugging info. But then you need to turn Wi-Fi off unless you're going to subtract it out of your measurements, which you can do as well. So that's another handy tip. Because if you leave it plugged into USB, you're going to think that I don't know what you'll think, but your measurements will be wrong. You might even get 0. I've gotten 0 before. I was like, 0? What the hell? So, all right, so now I'm going to do a demo. So I'll start with the oscilloscope. Okay, so this is a cheapy oscilloscope I got. It's a Taiwanese company. It's called Rigel. And for $300, I think it's a really good deal for an oscilloscope if you want one. So what you're seeing here are the measurements across the current sensor. So if I turn the phone on, I hope you can see this. You can see that now the power's gone up quite a bit, and now it went down because the phone turned off. So let me just turn it on, and I'm going to run this app I have that runs through some tests. So what's a good one? Do I have a cell phone on? I'll run a cellular test. So this test sends a bunch of UDP packets out over the cellular radio. So you can see how the power just spiked quite a bit. Here's my scale thing. Make it a little smaller so you can see it better. Let me run it again. I shouldn't have fiddled with it. Now it's... Oh, there we go. Yeah, so you can see the power that's going through the cellular. So cellular has a lot of funkiness with the power. That's why I decided to run that benchmark. But you could run something like a CPU, where you just run some software at 100% of the CPU. And that test will just look like a straight line. So you probably can't see this, but basically the power jumps up and then it stays at a constant power rate. So that's how you do that. So you guys can come take a look closer after the talk. It's probably hard to see, especially if you're over there. But that's my setup for the current measurement. Thank you. Thanks for your attention.